Magnets exert forces on one another. They're similar to electric charges. They can both attract and repel without touching. Like electric charges, the strength of their interaction depends on the distance of separation of the two magnets. Electric charges produce electrical forces, and regions called magnetic poles produce magnetic forces. If you suspend a bar magnet by its center, it'll act as a compass. The end that points northward is called the north-seeking pole. The end that points southward is called the south-seeking pole. More simply, these are called the north and south poles. All magnets have both a north and a south pole. For a simple bar magnet, the poles are located at the two ends. If the north pole of one magnet is brought near the north pole of another magnet, they repel. The same is true of a south pole brought near a south pole. If opposite poles are brought together, attraction occurs. Magnetic poles behave similarly to electric charges in some ways, but there's a very important difference. Electric charges can be isolated, but magnetic poles cannot. A north magnetic pole never exists without the presence of a south pole, and vice versa. If you break a bar magnet in half, each half still behaves as a complete magnet. Break the pieces in half again, and you have 4 complete magnets. Even when you break it down until your piece is 1 atom thick, there are 2 poles. This suggests that atoms themselves are magnets. Iron filings sprinkled on a sheet of paper over a bar magnet will tend to trace out a pattern of lines that surround the magnet. The space around a magnet, in which a magnetic force is exerted, is filled with a magnetic field. The shape of the field is shown by magnetic field lines. Magnetic field lines spread out from one pole, curve around the magnet, and return to the other pole. The direction of the magnetic field outside a magnet is from the north to the south pole. Where the lines are closer together, the field strength is greater. The magnetic field strength is greatest at the poles. If we place another magnet or a small compass anywhere in the field, its poles will line up with the magnetic field. Magnetism is very much related to electricity. An electric charge is surrounded by an electric field. A moving electric charge is also surrounded by a magnetic field. So where's the motion of electric charges in a common bar magnet? The magnet as a whole may be stationary, but inside it are atoms whose electrons are in constant motion about atomic nuclei. This moving charge constitutes a tiny current and produces a magnetic field. More important, electrons can be thought of as spinning about their own axes like tops. A spinning electron creates another magnetic field. A pair of electrons spinning in the same direction makes up a stronger magnet. Electrons spinning in opposite directions work against one another and their magnetic fields cancel. The magnetic fields of individual iron atoms are strong. Interactions among adjacent iron atoms cause large clusters of them to line up with one another. These clusters of aligned atoms are called magnetic domains. Each domain is perfectly magnetized and is made up of billions of aligned atoms. The domains are microscopic, and there are many of them in a crystal of iron. The difference between a piece of ordinary iron and an iron magnet is the alignment of domains. In a common iron nail, the domains are randomly oriented. When a strong magnet is brought nearby, there's a growth in the size of domains oriented in the direction of the magnetic field. Permanent magnets are made by simply placing pieces of iron or certain iron alloys in a strong magnetic field for an extended period of time. If a permanent magnet is dropped or heated, some of the domains are jostled out of alignment and the magnet becomes weaker. A moving charge produces a magnetic field. An electric current passing through a conductor produces a magnetic field because it has many charges in motion. The magnetic field surrounding a current-carrying conductor can be shown by arranging magnetic compasses around the wire. The compasses line up with the magnetic field produced by the current, which shows a pattern of concentric circles about the wire. When there's no current in the wire, the compass is aligned with the Earth's magnetic field. When there's a current in the wire, the compass is aligned with the stronger magnetic field near the wire. If the wire is bent into a loop, the magnetic field lines become bunched up inside the loop. The magnetic field intensity increases as the number of loops is increased. A current-carrying coil of wire is an electromagnet. Sometimes a piece of iron is placed inside the coil of an electromagnet. The magnetic domains in the iron are induced into alignment, increasing the magnetic field intensity.